So the third derivative law that we're going to be covering now is called the quotient law, and this is what you use when you have a quotient or when you have something divided by something else. So this is defined by our equation here, gf prime minus fg prime divided by g squared.
Oh, so that means if the G is girl and the F means friend, then it's girlfriend prime minus friend girl prime over girl squared.
I guess you guys could remember it that way. Okay, I'm going to show you guys how to use this in equation now. So we have the equation y equals x squared over 4x, and we're going to do the same thing that we did with the product law where we assigned an f and a g. So we have the numerator as f and the denominator as g, and we have the same thing where we have f and f prime, g and g prime, and we once again figure that out just using the power law. These ones are pretty simple. Now we can go ahead and just shove these right into the formula. One thing that's important is that you don't mix up the gf prime and the fg prime. Since there's a subtraction there, everything will be messed up if you flip those around. So you need to watch for that symbol right there and make sure that you're putting the right variables into the right spot. So we put in all our equation here. We have 4xf, f prime, and we went through that whole thing there. And I just wanted to point out right here in the denominator, we have a 4x, the whole thing is squared, as mentioned here. The entirety of g is squared. If there was a bigger function there, you don't square each individual part. It has to be the whole thing. And you never want to expand this, ever. If you have to think back and think to yourself, maybe I should expand this. It might simplify it. No, stop. Don't expand it because it can make it more complicated down the road. This could be used to cancel something out later in the question if the question lands out like that. But which it doesn't in this case, but a lot of the time you can cancel something with the numerator there, and you do not want to expand and have to do more work for yourself. So right away here, I just multiply these together to get 8x squared, multiply these to get negative 4x squared, and we were able to combine those into 4x squared, and then this is just the end of our question. Here's one of the more complicated derivative laws. It's called the chain law. It can only really get complicated because you have really big equations and you have chain laws inside of other chain laws and products inside of a chain. So I've showed you two simple questions here. You don't have to have the f and g thing here, but you can if you feel like that would help. So the chain law is the derivative of the outside function, but multiplied by the derivative of the inside function. And what by outside and inside, I mean if you have a function here, 2x plus 5, and it's all to the 4, the derivative of the outside is just a simple power law where you move the 4 down and you minus 1, so you end up having 4, the equation, to the 3. And that's just the derivative of the outside, but then you need to multiply it by the derivative of the inside. And our inside is 2x plus 5. And in this case, it's like we're ignoring the parentheses and our power, and we're just doing the derivative of this inside part here. In this case, you can once again just do the power law. So you take the 1 down and you minus 1, so you get 2 times x to the 0 disappears, and the derivative of the constant is just 0. So here we have our derivative of the outside, which I showed how to do earlier, and the inside, which we just showed. And you can easily multiply the 2 and the 4, getting 8, and that's the final equation. Something more complicated, but fairly simple once you memorize a lot of these identities, is trig. So the derivative of sine is cos, which is something I could show you how to do, but it's really not helpful in this case because this is just calculus. We're not getting really in depth with trig. But a lot of the identities for trig are set in stone. So we have the derivative of sine is always cos. The derivative of cos is always negative sine, and those kind of things are just kind of like that. So I didn't want to show you how to do that just in this simple equation, so I just showed basically what it is with trig. The derivative of the outside, it's like you're ignoring the angle for cos, or for sine. So you cover up the 2x, and you just turn the sine into a cos, and you keep the 3 there. The derivative of the inside is you're ignoring everything except for that 2x, and you just end up with 2, just like we had earlier here. And you multiply this 2 and the 3 and get 6 cos 2x. So now next up we're going to be doing implicit differentiation. This is called implicit because all the other derivatives we're doing are explicit. This is just definition words, it doesn't really matter what it's called, but this is implicit. And this is what you use when you can't easily isolate y. So y is in your function, like somewhere in the center, and you don't want to be using square roots or cube roots to try and get it alone, because now your whole function is going to be a chain with squares over it or cubes over it, things like that. So you can't easily isolate y, so you have to do something called implicit differentiation. And in this case, you're trying to isolate for dy dx. And dy dx is just the exact same thing as a derivative. It's the same thing as writing f prime or y prime or anything like that. So where you put dy dx next to any derivative that you find of a y. And you're finding the derivative of y in terms of x, and it's y on top of x for that reason. The derivative of y in terms of x, and that's why you only put it next to y. So in this example here, we have x squared plus y squared equals 25. You can find the derivatives of each individual piece simply by doing the power law. We have 2x and 2y, and you put the dy dx because we found the derivative of 2y, and then the derivative of a constant, which is still just 0. Now we want to isolate for this because we're trying to find this derivative. You can move the 2x over and get negative 2x equals 2y dy dx, and this still isn't alone, so you just have to divide by 2y. And the negative 2 and the 2 cancel out to just create a negative 1. So our final derivative is dy dx equals negative x over y. So now that we've learned how to find derivatives of polynomials and rationals, we need to also be able to evaluate the derivative of trig functions. So here I'm going to be showing you how to do them, all the 4 different laws that we figured out. So we have the product law first of all, and I have the function sine x tan x. The derivative of sine is cos, and the derivative of tan is sec squared of x. I did the same thing where I separated them into the housekeeping, where I have f prime, and g prime. And now I just follow the formula for the product law, which is f g prime plus g f prime. So you have sine x f, g prime sec squared x, g tan x, and f prime cos x. And you could simplify further with this using identities, but I figured it was too complicated to do that. And it's not really necessary for this, we're just trying to find out the derivative. And now I'm going to be able to find the derivative of the quotient here. I have g of x is negative cos x over tan 2x. This gets a little bit more complicated because now we need to do a chain in here, but since it's only a 2, it's not too troublesome. So we have f, which is negative cos of x, and the derivative of cos on its own is negative sine x, but since I have the negative there, it ends up being a positive sign. The derivative of tan x is sec squared of x. Forgot the 2 in there. That's kind of funny. And we need to multiply by the derivative of the inside, which is just 2, so we get 2 sec squared of x. And now we put it into the formula for the quotient law, which is gf prime minus fg prime over g squared. So I have g to tan x, f prime sine x minus, and since the cos is a negative, you need to add the opposite, and we get a positive there, cos x, and then I multiplied it by sec squared x, and it's multiplied by 2 here, so I just move the 2 to the front to make it a little less complicated. And then in the bottom, I made sure to divide by g squared, which is tan 2x, but you have to put the squared on the whole outside or else you're only squaring the inside. And make sure not to expand that. We don't really need to simplify this any further. If you were, you'd have to separate it into 2 components and it gets really complicated. And once again, we're not simplifying here, we're only finding the derivative.